based on electromagnetic induction. The animation shows a coil, which can be connected via an electric current meter to a voltage source. After applying a direct voltage to the coil, the electric current first increases fairly quickly, then more slowly, according to the inductance of the coil. Eventually it reaches a level resulting only from the ohmic resistance of the coil. The current creates magnetic fields that flow around every small piece of coil winding. The individual fields superimpose and form the total magnetic field depicted here in blue. If an alternating voltage is applied to the coil, the effective current through the coil is much smaller than when applying direct voltage. The reason for this is the alternating magnetic field, which generates a countervoltage in the coil by self-induction. The countervoltage in turn reduces the current consumption. Pushing an electrically conductive tube through the coil increases the effective current significantly. This is because the alternating magnetic field of the coil induces a current in the tube in circumferential direction, the eddy current. The eddy current in turn generates its own magnetic field, which counteracts the magnetic field of the coil. Consequently, the self-induction is low and the current consumption high. When a defect, for example a crack, comes into the path of the eddy current, the current consumption of the coil drops. The eddy current has to flow around the defect. The path of the eddy current is now longer, and the electrical resistance of the eddy current circuit is larger. This leads to a reduced magnitude and a reduced magnetic field of the eddy current. The self-inductance of the coil is increased, and the current consumption decreased. In practice, the alternating current frequencies are not as low as shown here for demonstration. They are much higher, typically in the region of some kilohertz. From now on, we're going to omit the magnetic field lines in the animation and represent the eddy current in a simplified static way. How does the technique work in practice? In eddy current testing with coaxial probes, the coils are either pushed coaxially over the workpiece or pushed through the workpiece. This is our simple test setup: the alternating voltage source, the electric current meter, the coil. Cables lead from the alternating voltage source to the electric current meter, then to the coil, and back again to the voltage source. Our sample is a tube made from an austenitic non-magnetic steel. We have purposely machined two cuts through the tube wall, one in longitudinal direction and one in circumferential direction. And here we go. The materials tester connects the return cable to the alternating voltage source. This closes the electrical circuit. The current consumption of the coil is still relatively low. Once the coil is positioned over the intact part of the tube, the magnitude of the current is high. The current decreases in the region of the longitudinal cut and reaches the original magnitude again in the intact part of the tube. The cut in circumferential direction has apparently no influence on the current. The animation shows the physical background. Low current consumption as long as the coil is still far away from the tube. The reason for this is the undisturbed self-induction. Much higher current in a region where the tube is intact. The reason here is the eddy current, its own magnetic field, and the reduced inductance of the coil. Smaller current consumption at the longitudinal cut, because the path of the eddy current is longer. The eddy current is lower and its magnetic field is smaller here. Full current consumption at the region with the saw cut in circumferential direction, as if there were no cut at all. The flow of the eddy current is almost undisturbed. Obviously, it is not possible to detect crack-like defects that run along the flow lines of the eddy current.